spend about 15-20 minutes to continue introducing the predictive analytics experimentation exercise for the class. And what I intend to do is to give you an idea the kind of the data that you will be getting. And then gradually we will onboard you guys starting Thursday for about a week, right? Before you actually get involved in doing any data analytics for the following 5 weeks. So that's the plan. And then the rest of the 1 hour, 45 minutes we're going to spend on, hopefully we will go far enough to introduce the model discovery backend, right? All the things inside the black box, the algorithm and everything, and the exercise to go through that together. And then we should be able to spend the next class, hopefully, to talk about the limitation and how you need to be careful if you decide to use those algorithms to do the model discovery, so that you will not get stuck on that, right? And so that pretty much would be what we plan to do today. Any questions before we start? And also I will give you an update that I finally finished studying your DSEQ paper summary report together with the grader. And I will try to give you more details about that to you guys. Probably next week, so that I will get some bandwidth in terms of covering the topic for the Chapter 9 model discovery before we do that. And so let me just share my screen so that you know what we are looking at here. Now, you should be able to see my screen. So pretty much they are like good questions that would be really, really helpful for me to talk to the class about things that may be new to you, and some of the great observations that some students have made when reading the paper, coming out of actually the misconception. And this is really great when you guys asked about that, so that we can clarify that misconception, right? So this is what I intend to do next week when we are done with the Chapter 9 or model discovery. Now, for those of you who turn in your alternative for COVID data analysis, I do plan to set up and one-on-one with your group to go over the comments that I provide. And also one person proposing genetic algorithm as an alternative, I need to talk to you because from the description, I did not see the fit, how that is relevant to our course topic at all. So I would need your help to justify and explain to me, right, why that genetic algorithm gaming project is relevant to this class, right? So those are the high-level announcements that I want to make. Now, instead of going straight to discuss the data for your project, right, I will keep that to the last, right? And instead, what I like to start today is to go over an example exercise with the class, so that everybody would think in, right, about exactly how we are going to do this. And the way that I want to do it is to follow through 2 website links. If you go back to the class notes on last week, so what I want you to do is, if you want to follow along, you may want to launch the link, right, that I put on the website, on the chat right now. Launch the one that I put it up, castle.com as well as this other one. Just launch it so that we can kind of like go through that together when we are doing the exercise with that. All right. So why don't I give you some time to do that to bring this one up if you want to follow along what we will be doing today. Okay. Now, and what we're going to do today primarily is just simply to focus on working through a simple example in Chapter 9 so that you can understand the in and out all these details inside the black box. How do we actually approach doing the model discovery, right? And last class where we ended up is to say we are going to formulate all the critical information that we want to capture in form of a algebra system, and therefore from that point on, what it is left is to solve that algebra system that is just a linear algebra system. And the way that we want to do that is to use singular value decomposition, right? That given any matrix A, doesn't really matter is invertible or a square matrix or not, you can always decompose that into three matrices. U times sigma times V transpose. U and V are orthogonal, right? And orthogonal, and sigma is diagonal, right? So that is where we left out at the end of last class. Okay, so what we're going to do today is to go through the singular value decomposition to convince you, right? This is a great idea that we can actually get the free lunch out of the singular value decomposition to find multiple solutions when your algebra problem is an underdetermined system that there are multiple solutions, right? So what we're going to do is to use the simple example in the book, right? It's a very simple case that you have two constraints that we enumerate that into John probability terms that we went through last time, and then we can formulate that into this matrix, right? A 3x5 matrix. And what we are going to do today is to actually apply singular value decomposition on A, right? So that you can get a hang on how the matrices U and V look like and how the diagonal matrix sigma look like. That makes sense? That makes sense, right? So, and the way that you would do about that is if you want to practice, just go to the first link, right? If you go to the first link, they actually have a singular value decomposition calculator there, right? And you can always use the arrow to expand the default matrix, right? And what you want to do is to create the matrix A, which is 3x5, and the default is a 3x4. You just need to click on the expansion arrow, right, to get one more column so that you get a 3x5 matrix. And then just copy and paste, right, the number of our matrix into it, right, which are 11001, 10100, and 11110. And after you do that, if you just click execute, right, it will return three matrices for you. The first one is a U matrix, which is a 3x5. The second one is a diagonal matrix. So, and the presentation here is that it just compressed that diagonal matrix into just one row. We'll come back to talk about that. And the V transpose matrix is just a 5x5 matrix, right? So therefore, if you just copy and paste the U matrix and the V transpose matrix, say, into your notepad or whatever, and then we write the result of the sigma matrix into diagonal form, right? So this is how it should look like. right? This is how your U matrix look like. So you just copy and paste from the result that returned by the SVD calculator. And then you will expand, right, that one row into a 5 by 5 matrix, right? And the V transpose is the same, you're just copying it over. And the way that you would expand your sigma matrix, right, into a diagonal matrix, all you need to do is the following, right? The first number is the 1, 1 entry in your diagonal matrix. The second number is the 2, 2 entry in your diagonal matrix. The third number is your 3, 3 entry in your diagonal matrix. And the fourth number is the 4, 4 entry. And the fifth is the 5, 5 entry. In general, each number is essentially just the II entry of the diagonal matrix. So if you rewrite that, this is how it should look like. So far so good, right? So what I want to do is to give the class maybe 5 minutes if you want to follow along, right? See whether you can reproduce, right? What you see right now here on the screen, right? That you use the SVD calculator with this as the input, right? The example from the book. Oh, I'm sorry. So I would just copy and paste things, right? Doesn't really matter the 0 is -0 or +0. If -0 is confusing, just put +0 there, they're all the same, right? And just put that in as an input for the SVD calculator and convince and verify to yourself this is the result that you got, right? And then we go from there, right? 5 minutes, right? See whether you guys can reproduce this error, this result. And if you have any questions on reproducing this result, just ask. And I'm going to stop the sharing in case if you have questions for me on the chat that I can see it, right? And at 9:35, then we will resume, right, to go over what you have here. So if any questions, you can either use the audio or you can use the chat to ask. Right, and then I will be able to either respond in the chat or through the audio. Right, so what we are doing today is to go through the practice. And I think we might have 1 or 2 visitors. And if you want to follow along, you're most welcome to do that. What we are doing today definitely is not going to be covered as a graduate center version, but we'll quickly go over that, but we will not spend clock hours to do this exercise. What was the input matrix? The input matrix is the one in the book. Right, so we are working through this simple example in the book, right? This matrix here, the 3 by 5, right? 1 1 0 0 1 1 0 1 0 0 1 1 1 1 0. Have you given us the data set we need for the second? No, not yet. We will save that for the last 15, 20 minutes, right? Depending on how fast that we can go through what we need to go through today. And you will not be getting the data set until the earliest Thursday, maybe later. I will talk more about that. So how are you guys doing? How many of you are done with getting the result from the SVT calculator right now? Okay, good. So now it's done. Okay, good. So we got a couple of people done. Right, let's give it another minute, right, for whoever wants to follow this part to finish it. Now, for those of you who are done with the downtime, right, so what would be also a good exercise is for you to convince yourself that the U matrix and the V matrix are orthogonal, meaning that if you actually take the U transpose matrix times U, this should be equal to the V transpose times V should be equal to an identity matrix, right? So if you want to test this part yourself, now is a good time to use a matrix multiplication calculator to do that. And if you go to the second link, right, it actually has a matrix multiplication calculator that we will be using momentarily, right? But in the meantime, if you want to convince that U and V are not just any arbitrary matrices, but actually are the matrices, right, that are orthogonal, meaning that the transpose is quote-unquote kind of like the inverse of the matrix. Now it's a good time to verify that for yourself. So anyone else is still kind of like working on the SVT calculator, or most of you or all of you are done with that part? Okay, good. So if you guys are done, right, so we are going to move on to the next part of that. Now, if you get your U, hopefully you have make up this presentation yourself, right? And if not, just do it. It's not a big deal. And copy over your V transpose matrix as well, right? And what you may want to do is the following, right? If you had a hard time to kind of like visualize how the V matrix look like, you may want to just go to the second link, right? The second link has a lot of like calculators there, and one is called matrix transpose. You can just use that to transpose the matrix. Essentially, what you are doing is simply flipping, right? Row becomes column, column becomes row, so that this is how it will look like. So far so good, right? So while you may be doing this or this, now what I'd like you guys to do is to convince yourself, right, that the three matrices, the U, the sigma diagonal matrix, and the V transpose are actually correct. Now, how do you prove it to yourself that these are indeed the correct answer? Now, if these are indeed the correct answer, then your expectation should be by multiplying the U matrix with the diagonal sigma matrix with the V transpose matrix, you should be able to get the original matrix back, right? So therefore, the next exercise is if you just simply go to the second link and get into matrix multiplication calculator, right? And if you just simply copying, say, the U matrix, and put that into A, and then you copy the diagonal, and you copy the sigma matrix into B, and say calculate, right? Then it will give you the product of the two matrices, and what you want to do is to copy the result, right? And then put it back as an input for the matrix A, right? And then for the matrix B, you are going to go back to copy your V transpose matrix. And if the answer that you get are indeed correct, when we say calculate, we should be getting a matrix that's the same as the original one, which is what we have, right, about this. All right, so why don't you see whether you can go through this to convince yourself that the singular value decomposition actually works.
It is. Of course, any kind of client-side.
And I'm going to drop off from the screen sharing and see if there's any questions on the chat, and I will come back.
But if you allow me to be aspirational and really ambitious here in Reach, I believe that HTTP.
You have audio issue. I would not be able. You should try to call in because I would not have time to retype everything that I say on the chat.
And printing the response text.
You may want to consider reconnect by dialing in using your phone, right? Which is what I did. Okay.
And so I've developed an API that hopefully can encapsulate that sort of essence. You have a URL. I'm using a service called HTTP bin. It's written by Kenneth Reitz again. We use a get request, a get function, and that just pings the URL and gets you the response, and you can print it immediately. Compare this to the equivalent call in libcurl. So if you've programmed in C before and you've had to do networking, there's a good chance you've used libcurl, and as you can see at the very top, there's a void star pointer. That's required for doing any kind of capturing of the response, and that's the easy interface. This is.
So are you guys able to verify and convince yourself the output three matrices that you get are indeed correct when you use the SVD calculator, right? And to verify that is that you just multiply the three matrices together to confirm that you actually get an A back.
The API is not written for people. When I use Poco, I feel like I'm talking to a computer. I'm a client. There's a server. I send this request object, and I get a response object back. So let's look at the same example. The simple GET request using Poco. And remember, this is a C++ library. Ignore the verbosity for a bit, and let's just kind of examine the semantics of what's going on here. At the very start, you have a URI object, which is sort of a generalization of a URL, and you pass it the string. You create the HTTP version, requires you to instantiate output stream, and then copy the input stream twice that we did earlier in our imaginary API. Is a verb-centric language. The issue
if you do not get it back, then somewhere along the line in using the SVD formulation is incorrect.
Is through a single API, a single function call, and use the objects to kind of modulate what happens inside the internals of that call. A little more power, and you just say, I want to use digest authentication, and it does it for you behind the scenes.
Right, so we got one person who was not able to reproduce A, right? I'm going to just share my screen. If you cannot get your matrix A back, you need to verify when you use the SVD calculator, you did not make mistake in entering the input, right? You don't need to do the 1.0000, you just put the integer there. And verify that this are indeed the result that you got. Right, your U matrix, your sigma matrix, and your V transpose matrix. Right, if you get the same answer and not able to get the A matrix back, then it probably is an error somewhere in the matrix multiplication. But if you get different results comparing to what you see here right now on the screen, then it's something wrong on the input, right, when you are using the SVD calculator. So far what we are doing is nothing more than just practicing what you already have learned, right, in your linear algebra class, except that we are lazy, just getting a calculator to do all the linear algebra matrix manipulations for us, right, and SVD decomposition calculator to do the SVD for us, right. So I want to make sure that we set the stage for that before we get to the meat of what we're going to discuss today. Let's see, anybody else didn't get, anybody else did not get the A matrix back? You probably want to verify your result, right? Check your input, output, and everything just to be sure that you are not making a mistake in copy and paste. Okay. Move on. Okay. So now what I want to do is to get to the meat of what matters when we talk about model discovery. Now, if you recall, one of the very important reasons why we decide to use SVD decomposition is because we have this nice property, right? Column vector I in matrix V is a null vector if the corresponding I entry in the diagonal matrix is 0, i.e. A times V sub I is equal to a 0 vector.
Professor, can you share the screen?
Oh, thank you. Yeah, thank you for reminding me. Okay. So let me do that. Come on. Right. So this is the key result, right? Key point that we're getting to right now. Okay. That we briefly talked about that, but really have not yet spent time to drill into the detail of that. The column vector I in the column vector I, we're going to call that VI, right? In matrix V is a null vector if the corresponding II entry in the diagonal matrix sigma, right, is 0. And what we mean by a null vector is that if you take the original A matrix and multiply with that vector, you will get a 0. Right, so what does that mean? This is what it means. So if you first look at your sigma matrix, right, your diagonal matrix here, the result. Now, what you notice is that the 2 entry here in this diagonal matrix and the 5 entry here are 0, right? So if the 2 entry is 0, 5 entry is 0, then what it means is that the second column of your V matrix and the 5th column of your V matrix is going to be a null vector. And what that means is that if you take the second column of your V matrix and multiply that with A, you should get a 0 vector. And likewise, if you take the last column of your V matrix and multiply with your A, you should get a 0 vector, right? And again, to convince yourself, all you need to do is to, again, use your matrix multiplication calculator, right? And just put your A matrix here and put your V sub I vectors there. And when you multiply these two, you should expect to get a 0 vector, which is what we have here. And similarly, if you plug in the last column, right, you will get the same. Did you see that? Right? So that is a key point, important result that we are going to take advantage of, right, in a moment. But I want to make sure that you can convince yourself that what we talked about in terms of the important property of the SVD actually is true and it works, right? And here is your extra credit opportunity. All right. And I would say first 3 in the class who can prove the key point will get extra credit. How about that, right? So rather than just simply using example to convince ourselves this is true, see whether you can actually formulate and prove it, right? Who can prove correctly, I should say. Right, and don't be sloppy, and it has to be correct. If it is not correct, it doesn't count. So don't rush, right? It's better to get it right. And that's your extra credit opportunity, right? To see whether you can just prove that this is the case. All right. Now, any questions at this point? Before we go further, why do we care about all this? Any questions so far?
Professor, can you see the key point again?
To say it again? To what?
The key point. Can you share your screen again? I just want to copy it.
You don't have to copy. I'm going to put that in the class note.
Oh, okay. Okay. Thank you.
Yeah. Right. Right. Whatever you see on the screen today, I would just put in the class note. What is the VI matrix? The VI matrix is the VI. First of all, VI is not a matrix. VI is a vector, right? So the way you want to think about that is to take your V matrix, right? And think about your matrix is actually just a collection of columns, right? So therefore, in your V matrix, you will have column 1, column 2, column 3, column 4, and column 5, right? So each column is just a vector, right? We call V sub I. And if you look at the null vector, right, from your V matrix, you are essentially looking for the column, right, with a corresponding 0 in the diagonal matrix. So say you look at the column 1, right, in the diagonal matrix, corresponding entry is 1, 1. Is this 0? No, this is not 0. Therefore, the first column is not a null vector. Now you look at the second column, right? Then you go back to, because it's the second column, you go back to the 2 entry of the diagonal matrix. Is it a 0? Yes. If this is a 0, that means the second column is a null vector. You pull it out and put it down here as a V2, right? And then you do the same thing for every column, right? And when you do that, then you would notice that the second column and the last column are the two vectors that are actually null vectors, right? And what do we mean by null vectors? That means each of these vectors, if you multiply with the matrix A, will actually give you a 0 vector. That helps? Is that clear to everybody, right, about what we have been trying to do so far, right? Okay, so now it comes to why are we doing all this, right? So let's step back. Take a look on why we're doing all this in the first place. We are doing all this because in our class in data mining, we are interested in discovering models, right, that can explain what we consider as the truth, right, or information that we need to preserve. And in this simple example, there are two facts, right, that we consider as a truth that we want the model to be able to explain. One being P of x1 equal to 0 has to be less than or equal to 0.65, and P of x equal to 0 has to be equal to 0.52, and then we just add the probability f, right? And then we talked about that last time. You can reformulate that just as a algebra system of the John probability terms. And therefore, the process of model discovery to discover model or models that can explain your facts, right, or your so-called truth, will be nothing more than just simply solving this algebra system, right, for P0, P1, P2, P3, and S, right? And in order to do that, we say, yeah, if you just we write that as a matrix multiplied with a vector equal to a constant vector, then this just becomes a simple linear algebra problem. And if we can solve this algebra problem, then we would know the solution for P0, P1, P2, P3, and S, right? And then we would have a model that guarantees it would explain this because that's when you started out anyway, right? And we say, okay, so how do we find the first solution? After we have gone through the SVD, right? And to find the first solution once you have all this, that's easy, right? If you say A times X is equal to B, then then you can just rewrite that as U times sigma times V transpose times X is just equal to B. Therefore, X is really nothing more than just simply V times, sigma inverse times U transpose times B, right? And then you get your X right away, right? And since you already know V transpose earlier, to get V is no big deal. We just do the transpose, we get our V. And what about our sigma inverse? Sigma inverse is easy, right? Whatever is a 0, you just put that as a 0. Whatever is not a 0, what do? The inverse is nothing more than just 1 over that number, right? So therefore, your sigma inverse right here is nothing more than just the 1 over, the 1 over, right? I think along the line I messed up the indentation. Let me just fix it to make it easier to see. That's what it really is, right? So if you know the sigma, you just go look up whatever entry is not 0, make it a reciprocal, and 0, keep it as a 0, then you get your sigma inverse. And if you have U, then yeah, to get the U transpose is easy, right? And let's just do that. Your U transpose is nothing more than just simply take your U matrix, right, and throw this back to your calculator. Right, the transpose. And calculate, and then now let the transpose calculator to give you back the U transpose. And now you get your V, right? You can just copy from here. You get your sigma inverse and you get your U transpose. If you just multiply these three together, you will get a solution for X. Why don't you try, right? See whether someone can help me to quickly multiply these three together and see what is the X you get. Anybody has figured out what X is? What do we have here? So anybody has figured out X? If you figure out X, just type it in the chat, right? So that we can continue. Now, for the matter of time constraint, I'm going to just put the X that I got. Hopefully this is correct. I was starting doing the same thing as you guys, like about 30 seconds later since I asked you to start doing it, right? So this will be your X. All right, so therefore, if you need to verify that the X is indeed correct. Let's make sure that our X is correct. All what we need to do is simply go back to with my A, right? Take the A, and when you multiply the A with the X that you get, right? We should get our B vector, which is 0.65, 0.52, and 1. Okay, so we are safe, right? Close enough, right? 0.65, 0.52, and 1. So therefore, right now, we know that, so this is one solution, right? And what does that mean? It means the probability model is essentially P0 is 0.2957, P1 is 0.2774, P2 is 0.2226, and P3 is 0.2025. This is just a slack variable that you don't care, right? For the purpose of your solution here. Right? For the purpose of this solution, you only care about P0, P1, P2, and P3. We don't care about the other one, right? So that's where we are about this. And so what we have done so far is that we can just apply SVD, right? So that is a genius idea. That we can figure out the U matrix, sigma matrix, and the V matrix, right? And then right away we can just like calculate the inverse, right, from the other side. Then now we get one solution. And to verify this one solution indeed is the correct solution, we just plug it back in, right, to convince ourselves this is the case. So far so good. Any questions? No, the solution is not unique, right? So that's a good question, right? Actually, the solution is not unique. Let's take a look back to our problem, right? So what is our problem here? Our problem here, if you look at it as an algebra problem, how many unknowns do you have? In this algebra problem, you have 5 unknowns, right? But you only have 3 equations. So what do you expect? Well, this is an underdetermined system, right? Because this is an underdetermined system, therefore, what do you expect? You are expecting many, many solutions. That makes sense, right? So far, all we have done is just to get one first initial solution. That's it, right? And now what we want to do is, how do we take that one initial solution to synthesize, right, many, many more multiple solutions for this underdetermined system, right, is what we're getting into, right? And how do we do that? Well, if you want to get another solution, right, let's call that Y. And guess what? If you just take your initial solution, right, and you add that to, say, some constant C, right, and multiply that with your V2. Oops. Can I do that? Ouch. I don't think I can do that. This is kind of like crummy. Sorry about that. We should have thought it through about that. Let me make this more prominent so that you know what is going on. Okay. So if you just take the first initial solution that you found, and you take your null vector, right, and multiply this null vector with some constant C, you can pick whatever C should be, right? You will get yet another solution. Right, and you can just keep doing that. Like, for example, maybe I don't know whether that works or not, right? Maybe try C equal to say, don't know what, right? And then just add these two things together, they will get another solution. And then you change the value of C, and you get another solution. You change the value of C, you get in another solution, and you will just get multiple solutions at that point, right? And I will let you guys verify this part yourself, right? So that I can spend the next 5 minutes or so to wrap this piece up, and then spend the rest of the time, right, to give you a second intro to the predictive analytics exercise and the data set. Okay. So your take-home exercise, right? Take-home exercise. Right? Can you find C, right, to derive one or more y such that A times y equals B? Okay. So why this is true is because how do you get y? The way that you get y essentially is just x plus a constant C times your null vector, right? And if you, by the way, just make a note for yourself, I will not be writing it right here. When we say C times this, it means you have to multiply this constant C to every single entry, obviously, right? Here you are multiplying a constant with a vector, right? So you are not just multiplying C with the third number. So you're multiplying constant with a vector right here. Now, so if you expand this expression here, this is just simply equal to A times X plus the constant C times A times vis-a-vis, right? So what do we know about A times X? Well, we know A times X is equal to B, right? We just verified that before. That X is a solution for this problem. If X is a solution for this problem, that means A times X has to be equal to B, right? That we actually verified that before. But what about the second term? A constant times A times vis-a-vis. We also have verified. What did we verify? Because your V is a null vector, the key point that we talked about earlier, right? A times the null vector is equal to 0. So therefore, this guy is just simply equal to this. If A times this, right, or A times Y is equal to B, what do we know about Y? Y is a solution for this problem as well, right? And every time when you change C, what happens? You get another solution vector here. So therefore, you can actually use this mechanism to synthesize multiple solutions at that point. That make sense? Right? Any questions about this? So that part will be the exercise. I will leave it up to you guys to do that at home. Right? And if any questions, just bring it back and then we will discuss about that next class. So far, so good? Any questions so far? Okay, good. So you guys should just make sure that you go home, right? Today we cover a lot of the technical details that you probably want to do some practice, spend some time review your algebra, make sure that you understand all this. Now, if this works, right, that this sounds great. Now, I'm going to say it again slowly. This sounds great. Does it always work? Under what assumption does it work, right? So under what assumption does it work? What is the assumption if we can generate multiple solutions? If A obviously has to be under determined system, right? The underlying assumption is that you can find an initial solution first, right? But where does this initial solution coming from? Well, your initial solution is coming from where? From multiplying the V matrix with sigma inverse matrix with U transpose matrix with the constant vector to get your X. Now, if you think it through this expression right here on the right-hand side, does it prevent anything? Or does it guarantee, right, that every value you have in the vector X is going to be non-negative? And the answer is no, it does not guarantee X to be non-negative, right? So what that means is that in this case, we got lucky that your initial solution, every value is actually non-negative, therefore we are good to go. But what if it turns out your initial solution, some values here are negative? Now, if you get an initial solution, some value here is negative, right? You just need at least one. Then this can no longer, this is a solution for the algebra problem that we were trying to solve. But that solution is not a solution for the original problem that you try to solve. Namely, we are trying to discover a probability model that we have additional underlying constraint, right? That all those terms have to be non-zero, right? So therefore, what are we going to do? If you are unlucky that your first initial solution is not all non-negative, then the answer for that is there's an algorithm, right, called Kusi-Shark-Sander algorithm. And this algorithm actually will guarantee you that you can always find a first initial solution that every term is non-negative. And that will be what we're going to do on Thursday. Right, so that's the intro for what we're going to do on Thursday, right? And if you know this too, then we know that if you properly formulate your constraint set, right, that this is a viable option for model discovery. There are other limitations that this may not work yet, but after we talk about that on Thursday, we will actually take a look on some examples, right, that why certain examples may not work, right? Most of the time that have to do with the way that you formulate the constraints, right? Or how do you state the fact or the truth that you want the model to explain. So we'll talk about that on next Tuesday. So therefore, what we will do is coming Thursday, we will look at this algorithm, right, called Kusi-Shark and Sander algorithm that will guarantee we will find the first initial non-negative solution, and then the following class we'll talk about the limitation, right? That will be all the time that we can afford to spend for this particular topic, right? Any questions before we switch over to talk about the predictive analytics experimentation that is coming up? Okay, if there's no more questions, I'm going to spend the next 12-15 minutes, right, to give you the introduction of the second part of the class, which is for you to get a hands-on experience, how do we actually do the predictive analytics, and the data that you are going to get. Let me share the screen first so that you can see. So this is a preview. We will keep talking about that until this thing ends in the next, I would say, 7 to 9 days, right, before you really have to do your number crunching. This will be the data that you will be getting, right? So we're going to give you a set of data that every record is a person with type 2 diabetes in our research project. And you will be getting the data about each person of the following. You would know the gender, you would know the age, you would know the ethnicity, you would know the income range, you would know the work, or I should say actually work and study hours, in case they are student or student working. Per week, you would know their own perception of their health condition. Make a note, it is about their own perception, is not their real health condition, right? But their own perception of the health condition. Their education level, and a 4x1 vector that try to capture their behavior readiness, right? How motivated they would do things, what is the attitude? How does it look like about their intention to actually act on something? Do they take ownership on what they need to do, right? As well as the data. It will not be 11 weeks. I do not know yet how many weeks you will get. I would give you a sample example. You will take a look the recommendation, so-called recommendation, and also what we call the engagement ratio. We think about that as just a metric measurement of like when you ask them to do things, do they really do it, and to what extent, right? So if you think about something like a student is similar to you as a professor, you ask a student to do things, do they do it, right? And if they do everything, what the professor asks, right, then the engagement ratio is 1. If the student does nothing, what the professor says, the engagement ratio is 0, right? So you will also be getting like engagement ratio on each week, right? So those are the basic attributes for each record that you will get. Cluster the population, I probably would just skip that. You would not be getting that. Your mission after the onboarding process in the coming week is to make the prediction for each person on the weekly basis. And you will be getting instant weekly feedback. How does it look like? This is how the data look like. Each row is a person. You would know it's male or female, the age, ethnicity, income range, how many hours do they work, what is the perception on their health, but not the actual health, right? They may think that they're in good health, but in reality, their health is poor, right? Or they may think that their health condition is terrible, but they are okay, right? At the education level. You will also be getting what we call the behavior readiness measurement, right? Essentially, it's going to be a number between 0 and 1. 0 means not motivated at all. 1 means highly motivated. Same for attitude, same for intention, same for ownership, right? And the recommendation for the purpose of this exercise would be something like this, right? So you are trying to help them to stay healthy, right? So therefore, you would target every week that you want the person to focus on improving their physical activity level. They maybe use to exercise more whenever you could, right? Or you want them to focus on the diet, right? Can you try to skip the cookie or the ice cream after the evening dinner as a dessert, right? And for each person, each week, that your mission is to give a recommendation. Do you want the person to focus on physical activity, exercise, or do you want the person to focus on diet, right? Now, and once you do that, then we will try to send that one out, right? See what patient would adopt that recommendation, and if they adopt that recommendation, then on the weekly basis, you get the instant engagement ratio number back, right? How well that they actually follow what you ask them to do on the weekly basis. And for the purpose of this class, right? You guys, we will give you the data that we have for each person, for whoever is going to be active, and you would only be doing 5 weeks. You would not be doing like 11, 12 weeks or longer, right? So your exercise will cover 5 weeks, right? Probably to start next week, right? So we should be able to finish the intro by Thursday for the students in Graduate Center. It's the same. We'll try to talk about that tomorrow. And then between tomorrow and the following Wednesday will be the onboarding week, right? That everybody can get used to this, ask questions, and then starting next week, right? You will have this data, and you will know who are the people here, what data we have about them already in advance, right? And then we will have you guys, right, to report back, like for this person for this week, what do you want to recommend to the person, right? And then we will actually do this live experiment for 5 weeks, right? See how well it works. Now, what would be the technique or idea that you can apply to come up with the personalized recommendation, right? The requirement is the same, right, as the students at the Graduate Center, but you can do in different degrees. The requirement is that you must apply at least one concept that we discussed in the class to make a prediction. Now, if you at the end say, yeah, I'm forced to do that, but you know what, Professor C's idea techniques really suck. I don't believe any of this works. I want to use mine. Is it okay? The answer is absolutely okay, right? Then at that point, you will be actually making 2 recommendations, right, or 2 techniques. One will be from the class, and the other one is your own one. Or you can do 2 to compare against each other as well. Right, and the reason we want to do that really is because you are not trying to help us to do better on this. This is a learning experience. For you, you may or may not pick the right one. It may not even work, and if it doesn't work, it may not even be your fault. It may be our fault that the patients that we have that simply cannot be engaged. Right, there are many other reasons this thing can happen. But if you are registering for this class, hopefully by the end of the semester, you know at least one concept we discussed in the class well, right? Well enough to say, well, this idea can be used for something, but when we use that for that specific something to solve that specific problem, it works or it doesn't work, and why, right? That really is the purpose of this second part of the class, why we are doing this, right? And therefore, by the end of the semester, the minimum expectation, if you pass the class, should be you should know at least one concept that we discussed in the class well, to the extent that you know how to use it, you know when you apply to this, does it work or not, and why, right? Not just whether it works or not, but why, right? So that will make up the major portion of your 40%, right? Or the 30% of your grade on this. So therefore, you want to focus. Don't be sloppy, right? Just do. I saw that in the DSCQ paper. Some of you just like really don't bother. Like, let me just copy some sentences from the original paper and turn it in, right? And I can promise you, if you do that, you ended up not knowing even one single concept in the class well enough to do this exercise, and then you are going to be in trouble at that point, right? So therefore, your job is to pick one concept, right? That you can do more than one, right? When I say one is the minimum, if you say, hey, I want to try these 3 ideas that I learned in the class, you are most welcome to do that. I will be excited to see that as well, right? And if you say, with my experience, nothing Professor C say would actually work for this, and that's fine with me too, right? And they say, my idea is going to work better than all of the ideas that you communicate, you teach us in the class, and that's perfectly fine, then try that. Right, so that at least you yourself can get a perspective, right, about how we actually do this in data mining, right? How do we do the EDA among different things, right? And that also makes sure that It's not like you register. I saw that even in my own class, students come to the class, say, you know what, I want to do my own project, fine. But in my own project, I want to work on something that really have nothing to do with the class, but I want to grade for this class, and that would not be okay, right? From the education perspective, my job is to at least introduce the minimum basics to the class, right? About data mining, therefore your job is to know at least one concept well enough that you can demonstrate in this second part of the experimentation exercise. Sounds good, right? Now, with the 1 minute left, I will not go into the details about some other numbers, but instead of have you hold up on, I'm going to share this with you, right? If you ever wonder, right? I don't know whether you guys can see my screen well or not. Can I do a slideshow here? Let me see. Oh, okay. So if you ever wonder, like, how do we actually do this experiment? How do we get all these numbers from, right? And I will briefly talk about that. I do not know whether they would let me do that. I would actually be giving a talk about our research project tomorrow at 12:15 for a class, a group of master's degree students in psychology department about this experiment. And the intention for that talk is to give the high-level overview. And for you guys, you're just working on one small part of it. Right, and if you want to know the overall picture, not just the work that you need to do on that exercise, I would ask whether they may allow you guys to attend. Right, if anyone is interested, shoot me an email. I will let you know the information, yes or no. And if so, what is the Zoom link? Right. So the way that this experiment works is this. So this is a study protocol approved by CUNY IRB. Right. So if someone approaches, say, hey, we're interested in this, then the first thing that it happens is that we will confirm that they satisfy all the inclusion criteria that I post in the Piazza, right? And if that all looks good, then they will fill out a survey for us. Not a DSCQ survey, but a survey similar to DSCQ. And from that survey, we actually will be able to derive what we call the behavior readiness, the motivation, intention, attitude, and ownership, right? And for the psychology student, that part or the DSCQ paper concept probably is what they are most interested in, right? And then once the person fill out the survey, we actually send them home and do nothing for 30 days. And 30 days later, they come back, right? And we make them to fill out the survey again. Right, and that before and after, there are two surveys on the first part. The first part is a survey of our own. The second survey is actually the DSCQ paper survey, right? And then 30 days later, they will fill out the DSCQ paper survey again. And after they fill out that survey again, then they will go for an orientation. And after they go through the orientation, then they will enter what we call the intervention phase. Now, in the intervention phase, they will be doing different things. Right, I will give you a demo of what they normally do next class, right? And then based on what we ask them to do, whether they do it or not, we calculate an engagement ratio, the one that you saw earlier in your data. And this study period is a minimum of 3 months, a maximum of 6 months. And at the end, they will fill out the DSCQ paper survey again, and then we will do an in-person debrief, right, about the experience. And then we do a 3-month follow-up after they exit from our study and a 6-month follow-up so that we kind of get a better idea about whether what we introduce here actually help them in their diabetic self-management. And the data that you guys are going to play with essentially is just the weekly data in this piece about what we call the intervention, right? And I will skip all the other details about the DSCQ survey and our survey, how we do the analytics, how do we do the customs, the population segmentation. Each one of this is going to be like easily 2-hour presentation I can give. So I would not be going through the details for the purpose of what you guys need to do for this class, right? But what you guys will be doing for this class is just focus on that one aspect of it. How do you make that prediction? What is the outcome look like? All right. So that is a high-level overview, and we will continue to talk about this next class. Any questions before we close it up for today's class?
Professor, so does each team get a patient, or does a student get one patient, or does the entire class get one patient?
Say that again.
Like you said that you're gonna give data of one patient, and we're allowed to like.
No.
ask
I'm
them
not
to do-
giving. I'm not giving the data of one patient. I will be giving the data of one group of the study participants.
Oh, and
You will not be getting one. Like for example, in this one you are looking at right here, right? This is a cohort of 22.
so does one
Each row is one
group
person.
get that cohort, and the other group gets another cohort?
No. The entire class will be getting the same data.
Oh, and you
Now,
said that
once we start on the weekly basis moving forward, you will start getting different data. Because that will be based on what data you analyze, how do you come up with your recommendation for the following week, what is the outcome for that week, the week after. That make sense, right? So the initial data set will be the same for everybody. But once we start the experimentation, moving forward, everybody may end up working on different data sets.
Okay.
All right. And the key really is don't try to do things like maybe we work as a group, right? Let's look into these two approaches and you submit one approach, I submit one approach. Just don't do that, right? Because you are trying to personalize for an individual, and this is real, right? And if we cannot understand what data you analyze, how do you reach that recommendation, we may not send that out to the subject, right? So I want you to be really taking a very professional attitude on this, right? And I'm not just looking for an answer, say, oh, I'm going to recommend exercise. I'm going to come back to you. For this, we have to come up with this recommendation. And then you're going to tell us that, yeah, I have this data set to start, I analyze, and this is how I analyze and get this result, therefore I recommend it. Right? And that pretty much will be the process we'll be going through for that 5 weeks when we are running this experiment. All right. And I will tell you more about this next class. Right. So now I'm just trying to gradually to onboard you guys into what you will be doing, because what you guys are doing is one small part of a much bigger study that they have like many other different interrelated components. Right. That you may or may not be interested, but if it matters for you to know them well, right, before you do this, then we'll spend time to talk about that, right, so that you get the full picture of the background about this, right? So that's what, and also the data that you saw earlier may not be the same group of people, because we are, that's the one I think about a week or two ago. Since we're doing rolling basis, by the time that you guys start, I do not know yet how many subjects and who they are. They may or may not be the same, right, at that point. Okay? And for those of you in the software engineering class, I would actually give you a little bit more background about this on the facet on touching the mobile app development part of this, right? But for this class, our focus is not on technology development, not on software development, but on data analytics. Right, so therefore, this is the only thing you need to focus. On the other class, they don't care about your data analytics, but more like, hey, if we want to enable that, how to enable a technology platform that we can do data collection. Right? So that in the other class, we'll talk about that. All right. All right. So we're 8 minutes over time. Any other questions before we continue the discussion again on Thursday? Okay, just check the Piazza or your check the Piazza. If I get the response back, whether they would welcome you guys to join that presentation to get more background information about the overall picture of this, I will let you guys know. Okay.
So this is the first shoe we got. We got the high top cream CDGs. These CDGs, I think they'll cost you only $135, but one thing with CDGs, you gotta run a size down. I wear 10.5, but for CDGs, I gotta wear size 9. And also CDG doesn't have they don't have half sizes. They only got whole size, so they don't have 10.5. They only got 10. Same thing, only got 9, 10, 11. They only got whole sizes. But you can find these anywhere pretty much. You get them online. I got these at Nordstrom. So yeah, just gotta note the sizing, and then also when you first get them, you gotta be careful with the toe cap because they get scuffed up really easily. But even though they get scuffed up easy, they're pretty easy to clean. So yeah, this is the first shoe, the high tops. Alright man, so next shoe we got the I gotta adjust one thing quick. Got the multi-hearted lows. These are probably my favorite ones because I just feel like the design was cool with like how the hearts are switching upside down, sideways. I think that was just like the best out of all the designs. And then I counted, these actually have 9 hearts. So yeah, if you guys didn't know, they got a lot of hearts on these. And one thing with CDGs, there's like not like the regular Converse toe cap. They actually got the glazed toe cap, which is one thing I really like about them. And then also the sole is like real squishy. So like obviously you can't feel it through here, but the sole is like thicker than usual. I feel like. Yeah, actually I can take it out. Damn, these are dirt. No, but these are dirty as hell. But they got the little extra layer, so the soles are like squishy. And so like for example, you'll be walking in like a city or something on a hot day, and then you'll come back, and the sole will be like molded to your foot. So that's the one thing I really like about them. They got the nice sole. The sole feels good, and then the glazed toe cap. That's another thing that I think looks really nice. But the only problem is they get scuffed kind of easily. You guys might kill me for this, but if you look around, like they have hella scuffs. But like they normally don't get scuffed this bad because I actually went to like a prom party and I was like jumping up and down. They absolutely murked, but easily. But so last but not least, we got the black OGs. These are the first pair I ever got. My mom actually put me on a CDG. She was buying like CDG shirts like way before they blew up. Like CDG shirts now are like $100, but my mom was getting them when they were like $30. That's beside the point. My mom, she put me on these. These are the first ones I ever got. They still got the glazed toe cap. Nothing's different about these between all the other ones that I showed you guys. They're all the same. For these ones, I noticed I can't take the sole out. I don't know why. Like maybe the glue like came loose on the other one, but I can't take the sole out on these ones. But yeah, same thing with the other ones. They got the scuffs, like the white ones. They got a couple of scuffs on the toe, but they're not that hard to clean. That's one good thing. They're pretty easy to clean. But one thing I say about CDG though, they're like way mainstream. Like everybody has them. Like people that are like into like some kids at my school, they're like really into fashion. They're like they'll have the CDGs, and then at the same time like plebs, like kids that like not into fashion at all. They like know nothing. They dress kind of weird. They got these. But I'm not trying to hate on anybody. You feel me? Like I support everybody. Like everybody's fashion thing. You gotta like wear whatever you want. You feel me? But CDG's pretty mainstream, but I still like them because you can get them in store, online, anywhere. But yeah, these are my first pair, and I still wear them all the time. I feel like these and the multi-hearted ones are the ones that I wear the most. But yeah, these are nice. These are real cool. I feel like the black and the red just looks super clean, and yeah. Alright man, so that's the end of the video. If y'all like the video, leave a like, leave a comment, subscribe, comment whatever new videos y'all want. That's all I gotta say. This song we